So welcome everybody to this week's HoloTube seminar. We are very happy to have Shiraz Minwalla with us today, and he's going to talk about, as you see from the slide, the Hilbert space of Chern-Simons matter theories. So welcome, Shiraz, the floor is yours.
Okay. Thank you very much for the invitation. HoloTube sounds like a fantastic initiative, and I'm very glad to be part of it. Okay, so my talk is titled The Hilbert Space of Chern-Simons Matter Theories. And my talk will be based largely on this paper that we put out last month, written in collaboration with my student Amyo Mishra and postdoc, my ex-student Tarun Sharma, and a postdoc Naveen Prabhakar. My talk will be based largely on this paper, but will make use of results derived in papers written over the last 10 years by various people, including our group. Some of the references for these papers are here. So let me start. Chern-Simons theories coupled to dynamical matter fields are interesting quantum field theories in 2+1 or 3 dimensions for several reasons. The first reason is just one of universality, or one of dimensional analysis, maybe I should say. As you know, in any theory, the term in the Lagrangian that has the smallest number of derivatives typically tends to dominate the dynamics of the theory at low energies. This is one way of understanding why the Yang-Mills term, or perhaps more precisely, the smallest dimension. Okay, this is one way of understanding why the Yang-Mills term dominates dynamics in familiar Yang-Mills theories. It's the term made out of the gauge fields that has the lowest dimension. So it dominates the dynamics at low energies. And if you came from a theory with some other from other terms in your Lagrangian, this term would anyway dominate low energy physics. Now in 2+1 dimensions, there is a term in the Lagrangian that has a lower dimension than that of the Yang-Mills term. And this is the Chern-Simons term. And so, if you've got a theory of matter coupled to gauge fields, and your theory does not preserve parity, then if you want to make a genericity guess as to what the dynamics of your theory will be at low energies, the guess should be that it will be a theory of the matter coupled to Chern-Simons coupled gauge field. Okay, so one reason to be interested in Chern-Simons coupled theories coupled to matter is just the generic in situations of theories that don't preserve parity, the generic dynamics you should expect for gauge matter systems at low energies. A second reason to be interested in matter Chern-Simons theories has to do with the nature of the coupling constant of Chern-Simons theories. Recall that the coupling of the Chern-Simons term. Recall that the Chern-Simons term is a dA plus 2/3 a cube with a trace, and the coefficient that appears behind the Chern-Simons term, which is sometimes written as k by 4π, that coefficient involves this term k, which, in order for the theory to make sense, in order for the theory to describe gauge invariant physics, k has to be an integer. Now, normally in a gauge theory, in a more familiar Yang-Mills type gauge theory, we write the coupling of the Yang-Mills term as 1/g². Here I've described how we write the coupling of the Chern-Simons term as k by 4π forget. So k times the Chern-Simons term. So you see that k is playing the role that 1/g² plays in a more familiar gauge theory. So what we see here is the fact that k is an integer tells us that the coupling constant of our theory is the inverse of an integer. Now that's sort of interesting. It's interesting for the following reason. The inverse of an integer is discrete, and so cannot continuously flow under the renormalization group. This tells you that Chern-Simons theories do not have non-trivial beta functions under the renormalization group. Now, because of that, it's very easy to make Chern-Simons theories coupled to matter fields conformally invariant. And so it's very easy to generate large classes of conformal field theories in 2+1 dimensions, which are gauge theories in which matter has been coupled to Chern-Simons theories. You know, the potential obstruction to this non-trivial, the existence of a fixed point, namely the beta function, one potential obstruction to the existence of a fixed point, namely the beta function of the gauge theory is not there. So it's very easy to make conformal dynamics. This is another reason that to be interested in Chern-Simons theories coupled to matter. A third reason now moves towards, physical aspects. When you take Chern-Simons theories and couple them to matter, the matter degrees of freedom turn out to have non-half integer spins. So what do I mean by that? Normally bosonic fields in 4 and higher dimensions, bosonic fields always have integer spins. Fermionic fields always have fermionic fields always, in some way of defining it, always have half integer spins. In 2+1 dimensions, however, it's possible for particles to have continuous spins that ranges continuously anywhere between 0 and infinity, or minus infinity, infinity. And when you study theories of Chern-Simons fields coupled to matter, this possibility is realized. The matter degrees of freedom turn out to have weird spins. Okay. Relatedly, these particles with weird spins obey weird statistics, and we'll see some of this in some detail as we go along with this talk. Okay. Other familiar rules when we're studying ordinary that we've sort of learned to expect from all quantum field theories by studying various examples, namely things like crossing symmetry of S matrices, also have weird modifications in these theories, weird and interesting modifications in these theories. So this is point 3 was basically to say that theories of Chern-Simons fields coupled to matter degrees of freedom are interesting because they display novel physics, physics that is not so familiar, and that makes them interesting. One more reason to be interested in these theories is that several of these theories have conjectured ADS-CFT duals. The most famous of these is, of course, the ABJM theory, which has a simple gravity dual description. There are other less standard dual descriptions for Chern-Simons theories with vector degrees of freedom, with fundamental degrees of freedom, which have been conjectured to have Vasiliev type ADS-CFT duals. Okay, so that's another reason to be interested in these theories. A fifth reason that only that we and others only became aware of once we started studying these theories is that these theories have an unusual sort of strong-weak enjoy invariance under an unusual sort of strong-weak coupling duality. The strong-weak coupling duality, and I'll have something to say about these theories, these dualities, they're not very much in the rest of this talk. The strong-weak coupling duality is one in which is a sort of play on level rank duality of pure Chern-Simons theory. It's an upgraded version of level rank duality of pure Chern-Simons theory. And it's roughly the statement that if you have a Chern-Simons theory with level k and rank n coupled to fermions, it is sometimes dual to another Chern-Simons theory of level n and rank k coupled to bosons. Okay, so it's a theory. It's a strong-weak coupling duality because the effective Toft coupling of the theory, namely n over k, is being inverted. So if one side is weak, the other is strong. But the new and unusual twist to this duality is it's also a Bose-Fermi duality. Once you do the coupling goes to 1 over coupling, you're forced to exchange bosons with fermions. This is the kind of thing that cannot easily happen in higher than 2+1 dimensions, but can happen in 2+1 dimensions, partly for some of the reasons we've mentioned. Okay, and lastly, the last reason to be interested in these theories is that in special limits, they're surprisingly tractable. The first limit in which they're very tractable is, of course, a famous one. When you take all the matter fields and send the masses off to infinity. In this limit, your theory reduces to pure Chern-Simons theory. Pure Chern-Simons theory was famously solved by Wheaton in about 30 years ago. and in his beautiful paper, he essentially explained how to compute almost anything you wanted to know about these theories. And everything was computable, but non-trivial, very intricate and very beautiful. Now, though Witten's solution of pure Chern-Simons theory was very intricate and beautiful, one might be tempted to regard it as not the kind of theory one wants to study for many purposes, because pure Chern-Simons theory is a topological field theory. It has no local degrees of freedom. There are no propagating gluons in pure Chern-Simons theory. The equation of motion for pure Chern-Simons theory is field strength is equal to 0. So that tells you that there are no propagating gauge invariant degrees of freedom. All degrees of freedom in pure Chern-Simons theory live either at boundaries or are associated with topology. Okay. This solution of Chern-Simons theory, 30 years old, has had lots of interesting mathematics associated with it, also interesting physics, particularly in its interplay with two-dimensional conformal field theories. Okay. However, what's sort of more recently understood is that there is another limit, another limit in which these Chern-Simons theories coupled to matter are exactly solvable. And this limit is one in which you take these Chern-Simons theories, you couple them to theories of matter with fundamental degrees of freedom, and you study them in the limit n goes to infinity, k goes to infinity with n by k held fixed. Or the way I've said it here is perhaps more precisely the way I'll look at it in my talk. You take n goes to infinity, k goes to infinity with n by kappa held fixed, where kappa is k plus sine k times n. So if every number in the game is positive, kappa is k plus n. Okay. So in this sort of total limit for theories with fundamental degrees of freedom, these matter Chern-Simons theories have been shown to be essentially solvable, more or less, maybe not exactly, but many quantities in these theories can be computed exactly in this large n limit as a function of this effective coupling lambda, valid from strong to weak coupling all the way to infinity, and you get many explicit and beautiful results. This will play a really important role in my talk today. Okay. Now, solvable theories are special. And the Hilbert space of solvable theories often has nice mathematical structure, which is sort of associated with these theories being solvable. Okay. In this talk, my goal is to explain to you that these matter Chern-Simons theories at large n with fundamental matter in the fundamental representation of un, and in this limit n goes to infinity, k goes to infinity, n by k held fixed, or n goes to infinity, k goes to infinity, n by kappa held fixed, also have a simple, tractable, but non-trivial Hilbert space. I want to explain that to you and explain some of the consequences of this fact. Okay, now the structure of this talk is going to be as follows. It's going to go as follows. What we're going to do is this. Over the last, almost 10 years, several groups, including ours at the Tata Institute, have, with increasing sophistication and with increasing generality, computed various quantities in these matter Chern-Simons theories. Among the quantities that have been computed are partition functions, finite temperature partition functions of matter Chern-Simons theories on S2 times S1. Okay. What I'm going to do in this talk is to just simply take the results of this path integral computation and, simply take is a bit of does a bit of an injustice what I'm going to plan. I'm going to sort of give you a little motivation for that result and then finally sort of state it. And in the rest of the talk, what I'm going to do is to then try to show you how that answer has a relatively simple and sort of, in my opinion, interesting Hilbert space interpretation. So that you can sort of use that answer to back construct the Hilbert space of the theories for which this partition function is computed. Okay, so that's the plan for the rest of this talk. Please do not hesitate to stop me with questions or comments at any point. Okay, so Now in our paper, the paper I cited at the beginning of this talk, we've studied basically every well understood example of these large N fundamental matter Chern-Simons theories. For the purposes of this talk, I will focus on one of these theories. Okay, this theory is the so-called regular boson theory. Okay, and what is it? Well, it's a theory of NB scalar fields. They have the usual kinetic term for scalars. There's a mass term, there's a 5 to the 4 potential, and there's a 5 to the 6 potential. Okay, all the terms in this Lagrangian preserve UN invariance. Okay, now this theory is not just a theory of matter, it's also a theory of gauge bosons. And the theory has the following property, that basically this derivative here is not just a derivative, it's a covariant derivative with respect to the gauge field. And the gauge field is self-coupled through a UNB level K Chern-Simons term. KB by 4 pi, trace integral ADA plus 2 by 3 A cube. Okay, so this is the Lagrangian that defines this theory, and if you want me to be precise, every term I quote here is, every formula I quote here is valid for the theory defined by this Lagrangian, coupled with a dimensional regulation scheme. Different regulation schemes sometimes require redefinition of the Chern-Simons level. This is quoted in the dimensional regulation. Okay. So in our paper we study, as I said, several other theories, but we'll focus on this one for the purposes of this talk.
Shiraz,
okay. Yes.
Shiraz, can I quickly ask? I'm sorry if you mentioned already, but what is the dimension of space-time that you have in mind?
Yes, I'm sorry, I should have said this more clearly. We're always interested in 2 + 1 dimensions.
Of course, yes. Great, thanks.
Yes, and the reason for that is that the Chern-Simons gauge term is only well defined, at least as I've stated, in 2 + 1 dimensions, right? Because it's ADA, so it's 3 indices, which makes a 3 form, or a cube. Actually, it's an interesting question. A question one could ask is, there's also a Chern-Simons term in 5 dimensions.
Yes.
So one could ask, could one make similar progress in 5 dimensions? Let's forget the matter. If you forget the matter to start with, just look at pure Chern-Simons theories in 5 dimensions. At first sight, it looks very similar to its 3-dimensional cousin. But once you start looking at the Lagrangian for 5 minutes, you realize that there are big differences. The main one big difference is the following. Chern-Simons, both in 3 and in 5 dimensions, are topological theories. Since they're both topological, they have no bulk stress tensor. So if you get a Hilbert space in your theory, all states in the Hilbert space will have 0 energy because the stress tensor just vanishes. So it's sort of very important for the consistency of pure Chern-Simons theory that the Hilbert spaces in any reasonable situation are always finite. Because if you had an infinite number of states at the same energy, that sort of probably is a recipe for sickness. A partition function, for instance, would just be infinity. Okay, and the reason that happens is that the equation of motion for pure Chern-Simons theory turns out to be F is equal to 0. And since field strengths vanish, that tells you that all solutions to the equation of motion are up to gauge transformations 0, at least locally. Yeah. So all your degrees of freedom come from Grobel stuff or from insertions and, Yeah. On the other hand, the equation of motion for 5-dimensional Chern-Simons theory is F wedge F is equal to 0. Now, it's perfectly possible for F not to be 0, but for F wedge F to be 0. And that tells you, and there's an infinite number of configurations. So that tells you that pure Chern-Simons theory, at least naively, has an infinite dimensional Hilbert space with all states at 0 energy. So it feels like it's a theory that will not be easy to make sense of. Now, if you add matter fields to that, this will regulate this divergence, but in a way that would be hard to get a tractable handle on. Yeah. Even though I feel it's a very interesting question and it's worth thinking about more. Right.
Yeah.
Right. So, but in this talk, we'll always be in 3 dimensions.
Okay. Great. Thank you very much.
Okay. Excellent. Fine. So now in the next few slides, what I'm going to do is to sort of roughly motivate the formula for the S2 times S1 partition function that we've computed for this theory. Now, the way we computed this formula was highly technical, okay? We used large N. We summed basically an infinite class of planar diagrams by recasting this summation as a Schwinger-Dyson equation. Turned out to be an integral equation. Turned out that for some reason that we didn't, at least at that time, I don't think we really understand well. It turned out it was an integral equation that by using some tricks, we could just solve, even though it was non-linear integral equation. And that allowed us to find this partition function. Now, that's a big story of its own. I'm not going to get into that. What I'm going to do is to just roughly motivate the answer that we presented. And then the rest of this talk, we're going to analyze that answer in great detail. Okay. Right. So the theory that we're looking at is this theory. And what makes this theory sort of challenging is this coupling to the gauge field. Okay. But to start with, just to get some sort of rough sense of what we should expect for, let's say, a partition function in this theory, let's drop the gauge field. Okay. So let's look at the just the theory defined by just the matter fields themselves. No gauge coupling. And the matter fields at large A. Okay. Now, in that situation, we would be looking at a theory of n bosons with this potential here. I've just rewritten the potential out here. Now, one of the effects of the gauge fields, as we've shown in a paper in which we computed the exact quantum effective action for the operator phi bar phi in this theory. One of the effects of this gauge field is to renormalize the local potential of this theory. Okay, and in the present context of this very simple theory, the renormalization turns out just as an exact statement at large n, all values of lambda to be extremely simple. All it does is change this coefficient of the cubic of the sextic term in the potential from x6 to +1 to x6 plus 4 by 3. Okay, so this is one of the results I'm going to appeal to. It will make no qualitative difference, but just to get everything completely precise. So what I'm going to do is just study the pure matter theory with its correct renormalized potential, namely x6 plus 1 replaced by x6 plus 4 by 3. Okay, so suppose I was interested in looking at the partition function of this matter theory with this potential, no gauge field, just as a 0th order try. Okay, the partition function of this theory is just sort of trivial to compute, as I now explain. At large n, the partition functions are trivial to compute, as I now explain. Suppose I take this action, I've just rewritten the full action of the scalar field, where remember I've just dropped all the gauge terms brutally at the moment. Okay. Now, this action here can be recast as an exact statement as the action for the same scalar fields, but coupled to a couple of Lagrange multiplier terms. So the Lagrange multiplier terms are sigma and CB square. Okay. The Lagrange multiplier terms have been added so that the equation of motion, okay, the equation of motion with respect to CB square, the equation of motion with respect to CB square tells you that sigma is equal to phi bar phi. CB square appears here and here, and so sigma is equal to phi bar phi up to some normalization. So NB by 2 pi sigma is equal to phi bar phi. Okay, so that's this equation here. Okay, and then now that we know that sigma is phi bar phi, all the interactions in this theory, which involved phi bar phi squared and phi bar phi cubed, can be traded for interactions involving sigma, and then these funny normalizations. Okay, so it's really that simple. It will take you maybe 1 or 2 more minutes to think through all the details. But once you perform the integrals over sigma, these path integrals over sigma and CB squared over the appropriate contours, you can really show just as an exact statement that these two are the same Lagrangians. Okay, now that we know that these two are the same Lagrangians, we notice that the matter fields here are quadratic in this Lagrangian. So we can just perform the path integral over the matter fields. That gives us a determinant. For general values of CB square some function, this is a complicated determinant. But we are interested in studying, let's say, the S2 times S1 partition function. And with a little foreknowledge, we realize that this partition function is going to be dominated by a saddle point in sigma. So if we make the plausible, in the CB square. So if we make the plausible assumption that CB squared on its saddle point is a constant, then we only need this determinant for constant value of CB square. And that determinant, of course, we know very well. It's just the determinant of a free scalar field of mass CB square. Okay? So if we, with some foresight, realize that we will only need this matter integral for constant CB square, that matter integral is trivial to perform. Once we perform it, you can rewrite it as a trace over a Hilbert space, namely the Hilbert space of free bosons. And you can recast this whole partition function into the following form. The partition function is written as the trace of e to the power minus beta h over the Hilbert space of free bosons of mass CB, dressed by some stuff. This stuff involves CB square and the other Lagrange multiplier sigma. And what one's supposed to do at large n, and at large n this is exact, is to compute this quantity and then extremize it over the two Lagrange multipliers CB squared and sigma. Okay? If you can do this you can solve this extremization problem, you've computed your effective partition function at large n. Okay, so you see that this theory is actually a very simple theory. It's closely related to free boson theory. All the interactions are dealt with, and large n makes this exact, in an effectively mean field type manner. Okay, great. Now the computations of this slide work in any spatial manifold. Let's specialize now for the rest of this talk to the spatial manifold being S2. So we're in S2 times time. Now, if we're in a compact manifold, we got this answer here by simply throwing away the gauge fields. Now, you might want to throw away many aspects of the gauge field interaction with matter, but there's one thing that you really shouldn't throw away, which is the Gauss law. One of the consequences of the gauge field interacting with matter is to impose the Gauss law. Okay, and if we ignore all other interactions, again crudely by hand, then how would this partition function be modified? Well, the crudest effect of this gauge field would be to include the contribution of the Gauss law. Now, the Gauss law, what does it end up doing? Ignoring all other interactions, the Gauss law takes this Hilbert space of the matter theory and projects it to the Hilbert space of SUN singlets. So projects the free boson Hilbert space down to its SUN singlet subsector. Okay, and that projection is enforced by an integral over a unitary matrix over the Haar measure, and then taking the partition function of the boson theory and twisting it with respect to the twist matrix U. Okay, so if we threw away every other interaction of the gauge field other than the Gauss law, this is what we'd find. We would find that that the partition function is the extremization of CB squared and sigma of not the free boson, not the partition function over a free Fock space of bosons anymore, but a free Fock space of bosons which march CB projected down to its SUN singlet sector. Okay, and there's a simple way to accomplish this projection, as I've indicated here. Namely, you take the theory, you couple it with respect to a twist, a unitary twist around the time circle, and integrate that twist over the Haar measure. And this is, completely computable object. Okay. So far, I've just thrown some crude guesses to you. Now, I told you that we've done much better than these crude guesses. We've actually computed this path integral exactly. I'm going to now tell you the exact answer. So the exact answer is sort of similar to the answer I've shown you. You remember that here we had this dressing factor times the trace of a partition, the partition function over a simple Hilbert space, namely that of free bosons. Here we have the same dressing factor times the partition function over a relatively simple Hilbert space, namely the Hilbert space of free bosons projected down to SUN singlets. Okay, The exact answer turns out to be, once again, the same dressing factor, but multiplied by something else. This something else turns out to be not too far from this object. Okay? Once again, what we get is the trace over free boson Hilbert space, twisted with u, e to the power minus beta h minus mu times q. Mu is a chemical potential, fine. But there are two differences. This, so far, identical to what we had here. The two differences are, first, in addition to this Hamiltonian, there's another strange-looking dressing factor involving a theta function which makes it look naively non-analytic, a strange-looking dressing factor. And second, that the integral here is not performed over the Haar measure, as was the case here, but over a strange measure. I'm going to tell you what this measure. So this measure I call DUCS. Sorry. I call this measure DUCS, the Chern-Simons modified Haar measure. And DUCS has the following structure. I'm going to explain what the structure is in the large n limit, because this answer is only correct in the large n limit. In the large n limit, the integral over the Haar measure can be recast into an extremization or an integral over an eigenvalue density function of the unitary matrix. The eigenvalue for density function, as usual, is defined here. Rho of alpha is simply sum over delta functions, locations of all the eigenvalues, and then divide by 1 over n. Now, in the large n limit, this funny looking discrete sum of delta functions becomes a continuous function. This is as usual. And this continuous function can take sort of any positive value anywhere in alpha space, alpha being between 0 and 2 pi. The Chern-Simons modified Haar measure is the same as the usual Haar measure, but with one additional constraint. This eigenvalue density function, which was always constrained to be larger than 0, has a new constraint. It also has to be smaller than 1 over 2 pi times mod lambda. Okay. So this is what comes out of long and difficult explicit computation, a relatively simple looking answer, an integral over a modified Haar measure, a twisted free boson partition function, coupled to a few extra factors. Okay. Comparing the exact answer with our crude answer, we see that the only correction that is needed is that this projection of the free boson Hilbert space to the singlet sector is replaced by this IB quantity, which I've described to you in some detail here. Okay. In the rest of this talk, I will explain that IB has a very simple Hilbert space interpretation. It is in fact the large n limit of the free bosonic Hilbert space restricted to the space of Wess-Zumino-Witten or equivalently quantum group singlets. Okay, in this talk, I will always work, to be precise, I will always work with the so-called type 1 UN theory. In this theory, the level of the Chern-Simons theory for the SUN part is K, while the level for the U1 part factor is kappa. The level is defined as the levels of the corresponding Wess-Zumino-Witten theories. Everything I say here has its generalization to SUNK theory as well as the so-called type 2 UNK theory. It doesn't matter. Okay, so now over the next 5 minutes, what I'm going to do is to explain to you what all the words in this in my statements here meant. Okay, what do I mean by the Hilbert space of free boson theories restricted to the space of Wess-Zumino-Witten singlets? Okay, so consider pure Chern-Simons theory in S2 times S1 with M Wilson lines, each at a distinct point on the S2, wrapping the S1 circle. Okay, no looping or anything like that, just simply wrapping these S1 circle. The Wilson lines in question are allowed to transform in the representations R1, R2 to Rm, where we demand that each of these representations are what sometimes called integrable. In the case of the type 1 theory, that means that the number of rows in the Young tableau cannot be larger than K. Okay. Now, over 30 years ago, Wheaton, in his famous Jones polynomial paper, demonstrated that the answer to this path integral, the answer to the path integral with these Wilson lines at different points of the S2 and then wrapping the S1, with the Wilson lines taken to be in representations R1, R2 to Rm, the answer to that theory was the dimension of the space of conformal blocks of Western-Witten theory with primary operators and representations R1, R2 to Rn on S2. Actually, this is true on any genus G manifold Riemann surface, but we will need this only for S2. Okay, now the number of conformal blocks has been, is computed by a famous formula by Verlinde. The same number can be computed directly using three-dimensional physics in a couple of other ways. One way is to follow the path integral evaluation of this quantity with Wilson loops and S2, done by Blau and Thompson in a beautiful paper written almost 30 years ago. We've generalized what they did in simple cases to the type 1 UNK theory of interest to us. Another way of doing the same calculation is to use supersymmetry. It's a lovely fact that supersymmetric N equals 2 Chern-Simons theory is actually physically identical to ordinary Chern-Simons theory, because the fermions that you have to add in the Chern-Simons action are non-dynamical, can just be integrated out. Okay, so quantities you can compute in pure in N equals 2 Chern-Simons, pure Chern-Simons theory can all basically allow you to compute similar quantities in pure Chern-Simons, non-supersymmetric pure Chern-Simons theories. And N equals 2 supersymmetric Chern-Simons theories can allow you to use the tools of supersymmetric localization to do some computations. So this is another way to compute the same quantity and find the same answer. Okay. Now, the reason I tell you about alternate ways to get well-known answers is that the alternate ways give you the well-known answers in a different representation, and a representation that will be more useful to what I'm going to be talking about. Even though you can, once you know the answer, it's not difficult to take the Verlinde formula and recast the answer directly into the form that we're interested in. So the answer turns out to be as follows. Okay, the number of singlets, the dimension of the space of conformal blocks is given by 1 over kappa to the power n times this factor, which is like a Vandermonde of the complex numbers, which are just phases actually in our situation, omega I and omega j. So omega I minus omega j, whole thing mod squared, and then a product of these quantities for I less than j. I runs from 1 to n. Okay, so these are like eigenvalues of an SUN matrix. You should think of these as eigenvalues of the holonomy matrix U that we were talking about before. Okay, and then multiply by the product of characters, just plain group theory characters, of the UN matrix whose eigenvalues are omega i's. Okay, and these characters are taken in representations R1, R2 up to R. All right. Okay. Now, this quantity is then summed over all allowed values of omega. Now, what do I mean by all allowed values of omega? In the case of the simple type 1 theory, all allowed values of omega I are simply the set of all possible omega i's that obey the equation omega I to the power kappa is equal to minus 1 to the power n plus 1, and no two omega i's are equal. You can see that had two omega i's been equal, this term would have set the contribution of that to 0. Now, if omega I to the power kappa if n is odd, then omega I to the power kappa is just 1. So what we're doing is summing over all inequivalent collections of n choices of the possible kappath roots of unity. When n is even, on the other hand, what we're doing is summing over all possible collections of n choices of the kappath roots of minus 1. Okay, so the famous Verlinde formula for the special case of type 1 UN theory can be recast in this form. And as I said, there are direct three-dimensional derivations of this formula, all of which we'll find in our paper. Okay, you see this very simple structure. And those of you who are sort of tuned into group theory will probably immediately realize that this structure here is very close to the Weil integral formula of classical group theory, which allows you to find the number of singlets in the product of representations representations. In fact, this formula here is can be thought of as a discretization of that Weil integral formula. The Weil integral formula just integrates eigenvalues over all possible phases. Here we look only at very discrete possible phases. Okay. Now, this discretization appears to approach the integral in the Weil integral formula. Okay. In the limit k goes to infinity, kappa goes to infinity, because in this limit, omega is all the, for instance, kappa roots of unity. Those roots become sort of dense in the circle. However, there is one, so you might think that in the limit n goes to infinity, k goes to infinity, kappa goes to infinity, n by kappa held fixed, the limit of interest to my talk, this discrete sum just simply reduces to the Weil integral formula. That's not quite the case. That's not quite the case because of the restriction that no two eigenvalues can be equal. Because of that, the density of eigenvalues in the situation is bounded from above. The density is 1 over the spacing of eigenvalues divided by n. And that becomes kappa by n. Because, 2 pi, kappa by n, and then there's an extra factor of 2 pi, doesn't matter that. Okay. This tells you that the eigenvalue density function in this theory is always bounded from below by 2 pi divided by lambda. So what we get is indeed the Weil integral formula of classical group theory in this large n limit with an extra constraint. This extra constraint is simply that the value, the modulus of the eigenvalue density function cannot exceed 2 pi divided by lambda. But, so I've written that here. But you see, this integral with the usual Haar measure, which is the measure used in the Weil integral formula, supplemented with this additional constraint that the eigenvalue density function density cannot exceed 2 pi by lambda, is simply this measure ducs that I introduced earlier in this talk. So you see that the restriction to the number that restricting to the number of Westermino-Witten singlets is simply accomplished by taking a twisted partition function of free bosons, okay, taking a twisted partition function of free bosons and integrating over the Haar measure, but with this new twist. What we really should have been doing is this. But in the large n limit, that's equivalent to integrating over a continuous measure, continuous eigenvalue densities of the holonomy, eigenvalues of the holonomy, but with respect to a modified measure. Okay, and that's precisely the measure that appeared in the formula I showed you before. So I have almost already explained to you that the formula I showed to you before was projecting down to the space of Westermino-Witten singlets. However, I have not quite explained that because you remember the formula I showed you before also had this extra funny term. Okay, and now I'm going to explain to you what this extra funny term, what the origin of this extra funny term is. Okay. The partition function over free bosons can be thought of state by state, right? That's a good way to think of free partition functions with statistics. Don't think of it particle by particle, but single particle state by single particle state. And thought of state by state as a product over partition functions. That's why it's a free theory. Now, for every single particle state, it can be occupied by fundamentals in our theory or anti-fundamentals. Okay, by phi is a phi bars. And so the full partition function over free boson twisted with this unitary matrix is this quantity. One such term for every single particle state and then product over all single particle states, where EA is the energy of the single particle state in question. Now, this denominator here can be expanded. This denominator, and I should have taken a product over A here, I apologize. This denominator here over colors. This denominator here can be expanded as a sum over characters of the unitary matrix, and we get the following expansion. You get the characters that appear here are the characters for the representations with 1, 2, 3, 4 boxes in the Young tableau, completely symmetrized, and this goes up all the way to infinity. Now, the partition function of the bosonic Fock space restricted to Wessamino-Witten singlets, at least when defined in one way, is not simply given by, this quantity replaced by the trace over the free boson Hilbert space. That's because this quantity here involves a sum with n going from 0 to infinity. But terms with n here larger than k correspond to non-integrable representations. And it's a well-known fact, demonstrated by Gepner and Witten, that there are no conformal blocks coupling non-integrable representations to integrable ones. So if we want to restrict to Wessamino-Witten singlets, we should do this counting, but also put an upper cutoff in the sum. We should cut off the sum at k. Okay, so the correct truncation of the free boson Fock space to Wessamino-Witten singlets is given by this quantity, with this truncation of all these denominators up to order k put in by hand. Now, sort of simple algebra is sort of you can use some simple algebra to show that the truncation to order k is the same as taking this untruncated quantity and multiplying by this compensating factor here. And when we take the log of this, so that we put in the exponent, we get the untruncated quantity plus this extra funny term. This should have had a -1 to the pi n, sorry. Okay. Now, in the large n limit, this extra funny term is simply the following. If y, this quantity here, y, is greater than 1, then this quantity is simply kappa times log y. W should have been y, sorry. Kappa times log y. Okay, but if y is less than 1, then y to the power kappa is just 0, because kappa is very large, the large n limit. And so this quantity is just 0. Okay, so this quantity that you get in the exponent is what you usually get, plus an extra term with the theta function times log of y. Now, the physical problem of interest, y is equal to e to the power minus beta e minus mu. Okay, and this tells us that this extra term only exists for those states with whose chemical potential is larger than the energy of the state. Okay. All such states only exist when you've taken the chemical potential and made it larger than the mass. Okay. So now when you add in this effect and sum over all states such that the chemical potential is larger than the mass, and do it carefully, you end up recovering this factor. Okay. So we've learned something important here. We've learned that the path integral expression is telling us that we're effectively doing this trace over an almost free Hilbert space, a free Hilbert space truncated to a set of Wessamino-Witten singlets, and part of that truncation is the statement that no single particle state can be occupied by more than k bosons. Now, there's something immediately interesting here. Remember that free bosonic theories are unstable at chemical potentials larger than their mass. That's because such theories have single particle states with energy less than chemical potential. Now, when your energy is less than your chemical potential, the Boltzmann factor, instead of becoming a suppression, this Boltzmann factor, instead of being a suppression, is an enhancement, because it's e to the power positive quantity, which tells you that 2 particles in that state contribute more than 1 particle, 3 particles contribute more than 2 particles, and 4 particles contribute more than 3 particles, and this never ends. So your ensemble is dominated by infinite occupation of these states, and therefore is ill-defined. Okay, this is the well-known Bose runaway sort of Bose condensation instability for chemical potentials larger than mass in a free boson theory. You see immediately here that the bosonic exclusion principle cures this instability. Because exclusion principle tells you that no matter what you do, you cannot occupy any single particle state with more than kb bosons. So if the chemical potential is larger than the mass, those states may get pretty highly occupied, but that occupation number will end at kb. So there's no runaway instability. So we see already from here that the boson stability of free bosons is going to be cured at all values of chemical potential by this bosonic exclusion principle, which is an interaction effect, but a very simple interaction. Okay, so let's recap. The partition function of large N matter theories is given by an expression of the same form as the ungauged counterparts, with the replacement of the Fock space over the free Fock space over to its Wess-Witten singlet projected counterpart. Now it's clear that the restriction to the Wess-Witten sector has a huge impact in the spectrum at low energies. Okay, this would be true even for the Gauss Law singlet condition. But what about when you've got very high energies, or you've got a very large sphere? These are sort of equivalent things. You've got a very large sphere at some fixed temperature, or very high temperatures. In that situation, the Gauss Law singlet condition sort of trivializes. That's because the Gauss Law singlet condition is one singlet condition for now, n square singlet condition, sorry, for on a Hilbert space whose exponential dimension is much larger than n squared. So n square conditions don't make much of a difference to that partition function. Turns out that the same analysis is not true for the Wess-Witten singlet condition. Okay, and I'm going to explain to you how this happens. See, suppose we are working at finite n and k. This quantity IB here, which is this quantity here plus the Bosonic exclusion principle, is a sum over various eigenvalue configurations. Now, in the limit that the volume of the sphere is very large, it turns out that this summation over eigenvalues is dominated by a particular eigenvalue configuration, sort of by a saddle point type effect. And the eigenvalue configuration that dominates is the set of eigenvalues e to the power I alpha I, where alpha I is given by this formula. Okay. Now, when that happens, this formula here for the partition function almost becomes very simple. You see, this formula was a product, was a sum over terms, each term of which was a product, one term in the product applying to any given single particle state. So product over terms in the partition function associated with each single particle state, and then that product summed. In this large volume limit, that summation goes away. It's dominated by one term. And so now the partition function here is just a product over partition functions, one associated with each single particle state. But as I've already reviewed in this talk, a partition function which is a product over partition functions, one associated with every single particle state, is typically the partition function one associates with a free theory. Okay? So it looks like that we've got a free partition function, but a different free partition function from one we're familiar with, because this eigenvalue distribution, the eigenvalue, saddle point eigenvalue configuration is not trivial. It's something non-zero. It's not identity. Okay? And turns out that you can take each of these single particle partition functions and perform a sort of expansion in characters, as I did before for these guys. Right? And this expansion goes as follows. You have the sum from R is equal to 0 to KB. That's the occupation numbers of each state. Remember, it truncates at KB because of the Bosonic exclusion principle. Okay? And you're weighted by e to the power R beta into EA minus mu. This is the Boltzmann weighting factor for R occupations of that state. All this is as expected. What's interesting is that you've got a coefficient here that is unusual. This coefficient DNS is the Q number analog of the choose function NCM, where Q is the number e to the power 2 pi I divided by kappa, And the Q number analog is defined by the n is n factorial, q with n factorial, m with n factorial, n minus m n factorial, where a Q number is defined by this formula, in case you've never seen it before, and the Q factorial is defined by this formula. If you've not seen this before, I won't have the time to explain this stuff to you in more detail. Yeah. Now, in the limit Q goes to 1, this becomes just the usual choose function, and we get the usual formulas of both statistics. Okay, but Q going away from 1 deforms away from this, the usual formulas of both statistics. We've got something new. Now, ignoring all details for a moment, an immediately striking aspect of the large volume limit, as I've emphasized before, is that the partition function is a product over partition functions, one for each single particle state. As I said before, this suggests that our partition function is that of a free theory, but a sort of weird free theory, because each single particle state has a partition function that's unusual. Now, it's not that it's a free theory is not correct. It feels like it, but it's not quite true. One way of convincing yourself of this is to notice that this expansion here, these DNSs that appear in this expansion here, these are, by the way, also the quantum dimensions of, well, it doesn't matter, quantum dimensions of the representation with n boxes symmetric. For those of you familiar with that. These DNSs are not integers. So clearly this is not a good partition function over a real Hilbert space. Okay, I'm going to explain to you what is actually going on. Something we establish in our paper is the following. There is a remarkable universality of the fusion rules of Wess-Zumino-Witten theory in the limit that the number of characters that you insert is very large. In this limit, the following happens. Suppose you fuse n1, n2, n3, n4, and nk representations of n1, n2, n3, n4, nm representations of Wess-Zumino-Witten theory at level k. Okay, you fuse characters, particular characters, and you ask, in this fusion, how many representations? You do the continued fusion of these representations, and now ask, in the final answer, how many representations of type Ri do I get? One of the things we demonstrate in our paper is that the number of representations of Ri you get from this product divided by the number of representations of Rj you get from this product is the ratio of the quantum dimensions of the representations Ri and Rj, where quantum dimensions are notions in Wess-Zumino-Witten theory, for those of you familiar with it. Okay. What's really interesting about this is that it's universal. It doesn't depend on what the details of the initial representations that you fused with. This universality explains why we got a product of partition functions. The explanation is simply that, well, I'm running out of time, so I won't give you that explanation. It's written on the slide, but it's an immediate consequence of this universality. Okay. Something else that I want to say, but I will also say it very quickly since I'm running out of time, is that this formula for the single particle partition function that I've written on the slide has an interesting property. If we keep kappa, which is n plus k, held fixed, and then vary k, so we keep the sum of n and k fixed, but we change k starting from 0 and then take it to infinity. Starting from 0 and taking it to kappa. So let's first start at k equals kappa. Okay, in this limit, and take every number to be large. Okay, in this limit, n is 0. N divided by kappa is 0 because all of kappa is k. Okay, and in this limit, these quantum dimensions reduce to the classical dimensions. So these quantum chooses become classical chooses, and you recover the ordinary formulas of both statistics. But in the other limit, the limit where k is taken to be not very large but very small, in that limit, turns out that these Q deformations turn into the chooses that you would get for Fermi statistics. Okay, in fact, you recover the partition function of KB free fermions in a single particle state. So there is a sense in which these statistics here interpolate between the usual formulae of free Bose statistics and free Fermi statistics. In the middle, they're neither. Okay. Now, these new statistics give you a lot of interesting physics. For instance, we all study as undergraduates that the number of particles in a particular single particle energy state in a free Bose ensemble, when the state has energy epsilon and when we've got chemical potential mu and temperature beta, that this is given by this famous formula. With these new statistics, this famous formula has a slightly complicated but not very complicated replacement. It's given by this function. Okay, similar results apply for fermions and respect duality. Okay, and so now just fine. I've said this before. Okay, so let me make. I will stop in the next 2 or 3 minutes. I'm sorry for going over time. Okay, so let me make 1 or 2 points clear. What's sort of remarkable is this: we started with this theory of bosons interacting with gauge fields, completely relativistic, could be conformal, could be massless, and we performed the path integral using some tricks. Now, the trick we used, one of the elements in the trick was to go to a certain gauge, light cone gauge, and then integrate out the gauge fields. And once we did that, we got a theory of pure matter degrees of freedom interacting with each other. But this theory of matter degrees of freedom interacting with each other had some local pieces. That was the renormalization of the potential that I told you about. But other than that, a highly non-local mess. And that highly non-local mess turned out we could deal with quite miraculously. What we're seeing here is that the whole effect of that highly non-local mess is to impose the Wess-Zumino-Witten singlet condition. The theory is that of a perfectly fine local matter theory whose only non-local interactions are those imposed by this Wess-Zumino-Witten condition. In this large and large K limit, that is the net effect of this gauge field in this theory. Okay, so I'm done. These are my conclusions. What we've demonstrated is that the partition functions of these Chern-Simons matter theories at large n where they're solvable have a very simple and very interesting structure. The structure looks, at least for practical purposes, like a new free limit, but with modified statistics. There are many questions that this throws up that I would like to better understand, but since I'm over time, I'll just leave the slide and ask for questions.
Thank you very much, Shiraz. That was very instructive and motivating. And you explained a lot of aspects and touched up on many topics. Thank you for that. So I should ask, do we have any questions?
I have a bit of a question, actually. So
please
go ahead.
So I thought that about this Bose-Fermi duality, what you do, like the intuition of what the legend was that you combine the boson and the monopole and you turn it into a fermion into a theory. Like, is there something like that happening here, or is it like?
You know, the kind of intuition you're talking about is sort of like for the U1 theory.
Mm-hmm.
Right. Now, the UN Bose-Fermi duality, especially when n and k are both large, is sort of different from this. The nearest analog of what you said is the following statement. Part of the dictionary of this Bose-Fermi duality is, let's take the SUN. First, you I think are talking about like an SUN U1 duality. Okay, the analog of that would be an SUN-K and UKN duality. Now, there is part of the dictionary of that duality says that the baryon of the SUN theory maps to the monopole of the UK theory. Okay, this in the n goes to 1 limit reduces to the statement that you're making. However, from the large n perspective, it's a very complicated and not the most simple statement. You see, the most simple statement, as we see from these partition functions, is simply that the that the elementary fermionic fields map to the elementary bosonic fields. Okay, the relation of this, there's some relation of this to what you described, and the relation goes as follows. Consider a monopole in the UN theory. Okay, this monopole carries 1 unit of flux, and so by the Chern-Simons equation of motion, which is kappa times F is equal to J, because F is equal to 1, I mean integrated is 1, the number of units of charge have to be equal to kappa. So every time you've got this monopole, it has to trap kappa units of charge. Now, when all numbers are very low, it could turn out that that kappa was 1. And so then the monopole will trap 1 unit of charge. On the other hand, the baryon on the other side also becomes like just one single object, because n is 1. So this monopole trapping charge and becoming the other particle is the U1 analog of baryon monopole duality, which there becomes in small numbers becomes very simple. Okay, but when n and k are both large, there is a more elementary thing, and that's the basic objects map to each other. The basic fields map to each other. Now, this statement you might think is not a very precise statement, because the monopoles and the baryons are gauge invariant, whereas the basic objects are not. However, there are ways of making it precise. For instance, one way is to compute the S matrices of these objects. You know, the electron is not a gauge invariant object, but you can compute its S matrix. And you can show that the S matrices of the bosons are the same as the S matrices of the fermions. So, you know, that's a much simpler statement than this other quantity, which is a complicated composite. And you need to deal with complicated composites if you're dealing with gauge invariance. I'm sorry, that was a very long answer. I hope it addressed your question. I hope it was intentional.
No, it is amazing. Thank you. And sorry, Matthias, I couldn't find where to raise my hand, so I just speak out of turn.
Yeah, please, anyone who would like to jump in and ask a question, no problem. Do as follow Nick's example. Actually regarding, well, since it's kind of related, let me jump in and ask a question about the Bosonic Exclusion Principle. I try to understand that a bit better from that side. So I understand the intuitive explanation that you give, that in the fermionic theory you have the fermionic exclusion principle, and that this bosonic exclusion principle is just the direct level rank dual of that. But I'm trying to understand it from the description that you gave on the bosonic side, and I'm in particular trying to understand, to trace it back to like how it might be related to these restrictions that are imposed on the theory. So is there any relation to that you could point out, what that makes that there's a restriction on the harm measure on, like, or where does it originate? Like where does this exclusion principle come from? Like, that's what I'm trying to see.
I understand your question. It's a fabulous question, and I can answer it only partially. So, so like the earlier question, it's a very good question, and I'll tell you what I know. So, you see, the question is confusing for the following reason. If you study Wess-Zumino-Witten theory and you compute conformal blocks, then there is this well-known result that conformal blocks involving non-integrable representations vanish. Okay, non-integrable representations in the case of let's say SUNK theory are simply those representations whose Young tableau have a first row which is greater than k, where k is the level of the theory. Okay, so if one takes literally the statement that one wants to truncate to Wess-Zumino-Witten singlets or quantum group singlets, it's the same thing, then any insertion involving non-integrable operator, operator with an operator in a representation whose first row becomes larger than k, should just be taken to be 0. Okay, this is just a statement of a definition. Okay, there are no conformal blocks. There's no dimension of conformal blocks where any of the representations is anything but integrable. Okay, this was demonstrated in a paper by Gepner and Witten, very early days of the study of Wessel-Minowit theories. So far so good. This sounds great, right? However, what makes this thing really confusing is that in our derivations, in all our ways of solving these theories, we perform an integral over holonomies. And the answer that we get involves an integral over holonomies with this modified Haar measure and this additional piece. This additional piece here. Now, what makes this confusing is the following. That what would have been really satisfying is the following. That if I just evaluated this quantity and I just substituted the character of any representation that was non-integrable, for instance, completely symmetric, M box completely symmetric for M greater than K. If I just put this in here, if I had got 0, then all ends of the problem would have closed up. What makes the answer to your question confusing is that's not the case. Even though in Wessel-Minowit theory, when you insert primary operators in non-integrable representations, you get 0. If you take the formula that computes these conformal blocks and analytically continue that formula to non-integrable representations, you don't get 0. Okay? Another way of saying that is that in pure Chern-Simons theory, if you evaluate the expectation values of Wilson lines, where some of these Wilson lines are integrable representations and some are not, as far as I can tell, you don't get 0. And this is something that has confused me a lot, but I've consulted every single expert in the world, including Witten and various other people on this. And though there's no very clear consensus, as far as anyone can tell, you don't get 0. Okay, maybe there's some subtlety that everyone's missed, but you don't get 0. Okay, so since our theory was gauge theory and we had, in some sense, path integrals that were sort of like Wilson line insertions on the sphere, it's very puzzling that that formula manages to produce this factor, and it does, which is exactly interpreted by these just truncating that sum at this. It gives the Wessel-Minowit answer, not the continuation of that answer to non-integrable representations. Now, it would be very satisfying to understand this from some point of view. One possibility I feel is that somehow all path integral evaluations of Chern-Simons theory in the presence of Wilson lines have missed a subtlety, some Gribov ambiguity or something like that, and once you account for that subtlety, you get 0. This is what I thought was likely a few months ago, but after conversations with several people, I've been hit on the head and told this doesn't sound likely, so maybe I should believe that. Okay, another possibility, which is something we're exploring actively, is the following. I've put it in my discussion. Another possibility is that this phenomenon comes about not from the pure Chern-Simons theory, where Wilson lines are just fixed, but once you include the fact that they can move around. So if we move a little bit away from pure Chern-Simons theory, now moving a little bit away from pure Chern-Simons theory is doing non-relativistic Chern-Simons theory interacting with matter fields. Now, non-relativistic Chern-Simons theory interacting with matter fields is a Schrodinger equation problem. But the Schrodinger equation is an interesting Schrodinger equation. Okay? One can formulate, maybe this has been done, I'm not sure, but it's not difficult to formulate this problem as a problem in which the wave functions are not, in mathematical language, I think people would like to, you might want to call a single valued section on the bundle of conformal blocks. Okay, this accounts for the fact that these conformal blocks have monodromies. And so this is something that I and some colleagues and students are working on at the moment. So we formulated the Schrodinger problem in this language. It's a beautiful problem, and one can use this language to show that the two Schrodinger problems are dual to each other, namely fermions moving on this space of conformal blocks on one side and bosons moving on the space of level rank dual. Okay? What we're trying to do now is to take the large n limit of this description. What I'm hoping to see, but we've not yet seen, is that when we take the large n limit, all the non-triviality of these conformal blocks go away, except for one thing, namely the Bosonic exclusion principle. This is what I'm hoping is true. And it's a very, you might think it's a very wishful hope, but it's a very clear mathematical question and we're looking at it. Sorry, I can't say anything more precise than that.
That's a great answer. Yeah, looking forward to it, to the paper. So thank you very much for the detailed answers and for the questions. Is there any more urgent question like that can be answered quickly? Because otherwise we would conclude the recording here because of the progress time. So actually do that. So first, thank you very much, Shiraz, again for the clear talk, and everyone else for the participation and questions. I'll see you all next week.